Okay, so I wanted to give you guys some pointers for solving equations and inequalities. Theoretically, you would have covered this in Algebra 1, but there are several things I want to remind you of or teach you for the first time. So let's look at an example here. So if we have let's actually get the pencil out here. All right, so if we have 2 times n minus 3 is equal to 4 times n minus 5. And they asked us to solve this, so this will be our first example. What I recommend on these is distribute the 2 on the left side here, so you'll get 2 times n, that's 2n. 2 times negative 3 would be negative 6 is equal to, and then we'll distribute the 4 on the right side here. So we'll get 4 times n is 4n, 4 times negative 5 is negative 20. And how you go from here, how you proceed to solve this is kind of up to you. Some people solve it differently than me. What I generally like to do is I like to keep the variables positive. So at this point, what we're trying to solve for is n, and we've got 4n over here and 2n over here. And so the question is, should we subtract 2n from the left to get rid of it? Or should we subtract 4n from the right to get rid of it? And generally, both ways are fine. You'll get the answer either way. I kind of like to keep my variables positive. So by that I mean, personally, I would prefer to subtract 2n from both sides. That's just me. Because what that allows me to do is it allows me to keep a positive 2n over here on the right. Like 2n minus 2n is basically 0. So you'll just have negative 6 on the left side here. 4n minus 2n is just 2n, and then the minus 20 comes down. So if you do it the other way, that's fine. You're going to subtract 4n from both sides, and you'll get negative 2n on the left. And then you'll have to divide by a negative, which is fine. I just prefer to divide by positive numbers. So now we're here. So now we've got negative 6 is equal to 2n minus 20. I'm going to add 20 to both sides because the goal here is to get the n all by itself. And so what we get now is equals, so negative 20 plus 20 is basically 0. So on the right, we just have 2n, and on the left, we have negative 6 plus 20, which is actually the same thing as 20 minus 6, which is 14. Okay, so when you get to here, hopefully you remember from algebra, we're going to divide by 2 on both sides. If you have 2n and you divide by 2, then you're just left with n. 14 divided by 2 is 7. So this would be your answer in that case. Okay, so that first pointer is just, I generally recommend having positive variables, but if you like working with negative variables, that's fine. Totally valid. You're more than welcome to do that. That's your prerogative. All right, let's look at another problem here. Let's say they give you something like 2x plus 6 over 3 minus 1 is equal to 5. Okay, so when you solve these, you've got several options. You can either add 1 to both sides, and that will get rid of the 1. That's probably what I would do. Some people like to multiply by 3 on both sides. So they'll multiply over here by 3, and they'll multiply over here by 3. And the reason for that is when you multiply this part by 3, it gets rid of the 3 on the bottom. So that's kind of helpful. So I just want to point out that there are several different ways you can do this. But generally, if you have something like this where only one thing has a fraction, I would recommend getting the whole fraction part by itself and then going from there. So I'm going to add 1 to both sides with the hopes of getting that fraction all by itself. So 2x plus 6 over 3 is what I have left on the left side here. Negative 1 and positive 1 becomes 0, and then 5 plus 1 is equal to 6. And so now we have the question of, all right, how should we proceed? Generally, if you are dividing by 3 here, I would recommend multiplying by whatever that amount is. So we're going to multiply by 3 on both sides. What that's going to do is, since you're dividing by 3 and multiplying by 3, these 3's essentially get rid of each other. Some people like to use the word cancel. Some people will say that that's an equivalent form of 1. Same thing. Okay, so what you're left with on the left side here is 2x plus 6. And on the right side, you have 6 times 3 is 18. I do want to say one thing about this, by the way. Some people, when they do this, they cross out the 3's, but they still multiply the top part by 3. Don't do that. The whole point of multiplying by 3 here was to cancel this 3. Those will just get rid of each other. Okay, so don't multiply the top by 3 and cancel the 3 on the bottom. You can't do that. Okay, and now at this point, we've got 2x plus 6 is equal to 18. From here, I would recommend subtracting 6 from both sides. So we're left with 2x on the left is equal to 12, and then I would divide by 2 on both sides. So you've got x is equal to 12 over 2, which is 6. Okay, so that's another kind of problem that you might see. Let's try some other ones. So these are everybody's least favorite fractions. So what if we have something like 2/3 x minus 5 halves is equal to x plus 1/5. And I purposefully made this kind of awful as far as the fractions go. So what I'm going to recommend on these is that you multiply by something that will get rid of all of the bottom parts of the fractions. Okay, so if we just multiplied by 5, that would certainly get rid of the 5 here. But the problem is if I multiply by 5 here, it's not really going to get rid of the 3. It's not going to deal with the 3. So what's something that I could multiply that would take care of the 5 and the 3? Well, if you did 15, if you multiply by 15 here, it would get rid of the 5. And then if you multiply by 15 here, that would cancel with the 3 as well. The problem is that we also have a 2 here. And this is why these problems are so difficult and why people hate them, is we need to think of a number that will basically get rid of the 3, the 2, and the 5 here. So when we multiply by it, so I'm trying to think of a number that when you divide it by, you have something and you divide it by 3, it gives you a whole number. That same thing divided by 2 gives you a whole number. And that same thing divided by 5 gives you a whole number. So there are lots of numbers that would make that true, but we generally like to get the smallest number possible to do that, right? Like certainly 300, if you divide it by 3, would be a full number. It'd be 100. 300 divided by 2 would be 150. 300 divided by 5 would be 60. But I'd rather pick like the smallest number possible to do that. And there's a really convenient strategy to find a number that will do this. And that is, if you take these numbers, 3, 2, and 5, and you multiply them together, so 3 times 2 times 5, it might not give you the smallest number that they could all divide, but it will give you a number that they would all divide. So 3 times 2 times 5 is 30. And so what we're going to do here is we're going to multiply both sides of this equation by 30. What that's going to do is it's going to get rid of the denominators, the bottom parts of those fractions. Okay, so generally what I recommend doing here is I'm going to have 2 over 3. I'm going to leave the x there. And this is a little long-winded. Some people will just cancel the 30 with the 3, and they'll put a 10 on the top. But I like to just show you how this works very thoroughly. Okay, so I've distributed the 30 here. Now I'm going to distribute the 30 over to the negative 5 halves. So I'm going to do minus 5 over 2. And then I'm going to leave myself some room here to multiply by 30, because the 30 needs to go to both parts. Okay, next. All right, so that's the left side, equals. I'm now going to distribute the 30 to the x and to the 1/5. Okay, so now we've got, over here we've got 30x, and then plus 1/5. And then we're going to multiply that by 30 as well. And so what happens here is the 30 on the top is going to I would recommend multiplying here. Some people will cancel. They'll say, hey, the 3 and the 30 makes 10. Look, there are lots of different ways you can do this. I'm just going to multiply the top parts and then simplify from there. Okay, so on this fraction here, 2 times 30 is 60. So I just have 60 over 3x minus, let's see, 5 times 30 is 150 over 2. And that's equal to 30x plus, I'm just going to write 30 over 5. Okay, and so now what we can do is we can just start to simplify these things. Okay, so 60 over 3 is 20, so we have 20x minus 150 over 2 is 75. That's equal to 30x plus 30 over 5 is 6. So now we've got a relatively basic algebra problem to solve. Like I recommended before, I like to have positive variables, so I'm going to recommend subtracting 20x from both sides so that you're left with negative 75 is equal to 30x minus 20x is 10x plus 6. And then if it was me here, I would subtract 6 from both sides. And I'm going to end up with 10x here on the right is equal to negative 75 minus 6. That would be negative 81. And then from here, we will divide by 10 on both sides. So when you do that, you've basically just left with x is equal to negative 81 over 10. I'm cool with that as a solution. Some teachers would rather you put negative 8.1, but I'm cool with that as a solution. So, all right, so that's that problem, a problem like that. Next thing I want to talk about is when you get solutions that are really weird. So here's a problem that gives you a really weird solution. If you have, this is our fourth problem, if you have 4x plus 2, and we say that that's equal to x plus 3x plus 2, and they ask you to solve, and you're like, okay, cool. So what I'm going to do is I'm going to actually leave the left side alone, 4x plus 2, and say that that's equal to, I'm going to simplify the right side, so I'm going to get 4x plus 2. And from here, I'm going to subtract 4x from both sides. So minus 4x minus 4x. And when I do that, what I get is these cancel. So I get 2 is equal to, those cancel. 2 is equal to 2. And this is really weird, right? I'm kind of like, what? 2 is equal to 2. Where's the variable? Well, the problem is that the variable dropped out when you subtracted by 4x on both sides here. So if you get something like this, where you get 2 is equal to 2, the question on problems like these, so let's go back a little bit. So let's pretend that this stuff hasn't been done yet. If we go back to the original problem, what we're trying to do is we're trying to find values of x that make this true right here. Okay? So when you solve a problem, what you're doing is you're finding numbers that when you put them in where the x is, it actually makes the original equation true. This is the original equation. This is an updated equation, and this is an even more updated equation. Okay? So the question is, what values of x make 2 equal 2? Which is really weird because 2 always equals 2. And that's kind of the idea here. So what we say here is that this has an infinite number of solutions. We'll just say infinite solutions. The reason is because it doesn't matter what you plug in back in the original equation here for x, it will always work. And if you don't believe me, try something for x. So if we have 4 times, 6 plus 2, is that equal to, if x is 6, then we're going to say 6 plus 3 times 6 plus 2. Okay, so we're just trying 6 just for the heck of it, because apparently there are a ton of numbers that work here. Well, let's try this. So 4 times 6 is 24 plus 2. Is that actually equal to, so I'm going to put a question mark here. I'm saying, is this actually equal to 6 plus 18 plus 2? So 24 plus 2 is 26. Is that actually equal to 6 plus 18 plus 2 is 26? Yeah, so 6 actually works. Okay. Now, the funny thing is, if you try literally any real number for x back up in this original equation, it would work. That's why we say that there are an infinite number of solutions. So as a general rule, if you get something that just straight up equals itself, your answer is going to be infinite solutions. So for example, if you got 2x plus 1 is equal to 2x plus 1, you can actually just stop right there and say, hey, the answer here must be infinite solutions, because 2x plus 1 always equals 2x plus 1, no matter what x is. Okay, what about something that has, so this seems obviously true all the time. What about something that seems weird and would never be true? So what if we do 3x is equal to 5x minus 2x plus 4? And we ask you to solve that. Okay, I'm going to move the screen over. Oh, nope. Move the screen over a little bit. So let's simplify this a little bit. 3x is equal to, okay, 5x minus 2x is actually 3x plus 4. And then if we're just, not paying attention, what would we do next to solve? I would probably subtract 3x from both sides. And from here, what would happen is you would get, those go away, that becomes 0. So basically on the right side, you have 0 plus 4, which is just 4. On the left side, you've got 3x minus 3x, which is 0. And now you've got this weird situation where you've got 0 is equal to 4. And the question is, what values of x, if I plug them in, would make 0 equal 4? Which is kind of a dumb question. The answer is nothing. There's nothing you could possibly plug in for x that would make 0 equal 4. And the reason is, if you go back to the original equation, literally nothing that you plug in for x would ever work here. You could try any real number you want all day, every day, nothing would ever work. And so when you get a situation like this where it makes absolutely no sense, you would say no solutions. Because it doesn't matter what I plug in for x, it's not going to work. And you can kind of see why that is. When we simplified it the first time, we got 3x is equal to 3x plus 4. How could something be equal to itself plus 4? That just doesn't make any sense. There's nothing that would make that work. So the next thing I want to talk about is inequalities. So let's make a new page here. So you can imagine if we had something, this is our sixth example. Let's say we had something like negative x is less than negative 4. Okay? And basically, the too long didn't read version of what I'm about to tell you is that if you ever multiply or divide by a negative number while you're working out an inequality like this, you have to flip the inequality sign. Okay? But I want to try to offer you a convincing reason for why this is, because if you understand why, you'll be much more likely to remember this. And I remember when I was in high school, this was one of the things that I always forgot. When I multiplied or divided by a negative, you have to switch the sign. So I want you to think about this with me for a second. What it's saying here is that we have some number, and when you take the negative of that number, the result is less than negative 4. So what I've done is I've drawn a number line here, very basic number line. I've only put 0 in there. But I want you to imagine if negative 4 was right here. And I want you to just think for a second. So when we take the negative of whatever our number is, we need that to be less than negative 4. To be less than just means that you are to the left of something on the number line. So if we're less than negative 4, that means we are falling in this green area over here. Anything in this green area, extending forever to the left, would be less than negative 4. My question is, what kind of numbers, if you took the negative of those numbers, would actually fall in this green area? So what I'm going to recommend we do is we come over to positive 4, and I think that will kind of answer our question. I want you to imagine all of the numbers in the blue area here, this blue shaded area, if you took the negative of any number over here, like let's say 5, for example, 5's right there. If I took the negative of 5, where would I end up? I would end up at negative 5. What if I take the negative of 6? Where would I end up? I would end up at negative 6. So I'm going to say any number in the blue zone, if you took the negative of it, you would end up in the green zone. So literally any number in the blue zone would satisfy this original inequality that we have here. So if you took the negative of it, it would happen to be less than negative 4. It would fall to the left of negative 4. That's why when we divide here, so if this was just negative x is equal to negative 4, what would you do here? You would divide by negative 1 on both sides, and you would call it a day. You would get x is equal to positive 4. The problem here is that we're dealing with something that is not equal. It is unequal. That's why we call it an inequality. Okay, so what we're going to have to do here is we're going to divide by negative 1 on both sides. And when we do that, negative x over negative 1 just becomes x. But what you need to do here is this inequality sign here. Right now it says that this quantity is less than this quantity. That's how we read that. We need to flip it to say that x is now greater than, and then if you look at negative 4 divided by negative 1, that would give you positive 4. Okay, and if you think about this, the converse of this, think about something. I'm going to do it red because red's bad. We don't like the red here. What if you took like 2? If you took the negative of 2, where would you end up? You would end up at negative 2. But would negative 2 satisfy the condition of being less than negative 4? It would not. So what that means is that 2 must not be part of the solution set, which makes sense because the solution set is only this blue area over here, and it extends forever to the right. Okay, so maybe you didn't need to know all that, but that's kind of helpful for understanding why. So this is really important. I'm going to write this out. Sorry, I write really slow. If you multiply or divide by a negative number, while solving an inequality, you must flip the inequality symbol. All right, so now that I have hammered that idea in, let's look at another example here. So if you have 2x plus 4 is less than or equal to 5x plus 16. Again, personally, I kind of like to have positive variables, but just for the sake of what we just talked about, I'm going to actually subtract 5x from both sides just so that I end up with a negative variable. So 2x minus 5x is negative 3x. The plus 4 doesn't change at all. Since I'm subtracting here, I don't need to flip the sign. It's only when you multiply or divide by negative that you have to worry about flipping the sign. Now I'm here. So if I've got negative 3x plus 4 is less than or equal to 16, I'm going to subtract 4 from both sides. I'm trying to get this negative 3x all alone by itself. So negative 3x is less than or equal to, that right there is 0. All right, 16 minus 4 is 12. So now we're at this point, and we've got the x almost by itself, but we need to divide by negative 3. And here it is. We're dividing by negative. So when we do this, we want to say x is greater than or equal to, because we're flipping the sign. And then let's see, 12 divided by negative 3 is negative 4. So this right here is our solution. Let's look at another example here. So example 8. And this is going to be 6x plus 8 is greater than or equal to 4x plus 2. And I'm going to subtract 4x from both sides. When we do this, we get 2x plus 8 is greater than or equal to, that's 0. The 2 comes down. Let's subtract 8 from both sides. And we get 2x is greater than or equal to -6. And now we're here, so now we have to divide by 2 on both sides. The reason I'm putting this example in is because a lot of people freak out and they say, uh-oh, we have -6 divided by 2. Well, isn't this a negative? Are we dividing by a negative? And I'm saying, no, we're not dividing by a negative. We're dividing by +2. So it's only if you are actually dividing, like the number that you are dividing, like right here, if that's negative, then you need to flip the sign. You're just dividing by 2 here, which is a positive number. So don't worry about flipping the sign here. So in this case, we would get x is greater than or equal to -3. So that would be our answer in this case. Okay, the last thing I want to talk about is how to graph inequalities. All right, so how to graph inequalities. So let's look at our 9th example here. If we have 2x minus 1 is greater than or equal to 5, let's go ahead and solve this. So I'm going to add 1 to both sides. So this gives us 2x is greater than or equal to 6. And then we'll divide by 2 on both sides. And we get x is greater than or equal to 3. Okay, so what we've done is we have an original problem here that we're working with. And what it's saying is that I'm thinking of if you do 2 times a number and you subtract 1, I want that result after you do that to be at least 5. I want it to be greater than or equal to 5. And the question is, what initial numbers, if I plugged them in and doubled them and subtracted 1, would give me more than 5? More than or equal to 5. And the answer here is, look, if you plug in any number that's greater than or equal to 3 and you double it and subtract 1, we guarantee that you'll get at least 5. Okay? So the solution here is not, we're not saying 3 is the solution. We're saying literally every possible real number that's 3 or greater would work here. And so all we're going to do when we graph this is just visually show people the reality of this situation. Okay, so here's number line. Honestly, I don't label the entire number line. A lot of times what I'll do is I'll just put 3 here, like the number that I'm interested in. And I'm trying to indicate for my reader or whoever's looking at this that any initial number that's 3 or greater would work here. So what we do to do that is we just go ahead and put a little dot and we shade it in, and then we shade anything greater than 3. So we'll just draw an arrow to the right. And what we're doing is we're just indicating for our reader, hey, anything over here, you don't need to shade that in like I just did, but I'm just trying to show you visually, anything over here would work, including, by the way, 3, which is why we shaded it in. Okay, so this would be a great solution. This would be the symbolic notation. And if I asked you to graph, this right here would be your graph. Okay? Let's look at another example. So if we have 3x plus 6 is less than x plus 10, then let's solve this. So if it was me, I would subtract x from both sides, trying to keep positive variables. So 3x minus x is 2x, plus 6 is less than 10. And then we need to subtract 6 here. So we would get 2x is less than 10 minus 6 is 4. Divide by 2 on both sides, divide by 2 on both sides. So we're left with x is less than 2. Okay, so that is our solution. So if you're wondering, hey, what values of x, if I took 3x plus 6 and I wanted to make sure that it was less than the original x plus 10, what numbers of x would make that work? Well, apparently, if you plug in anything less than 2, that would make this inequality true. Okay, so let's graph that. So how would we graph that? We would draw a number line, And I'm just going to put in the number 2 here. And then I'm just trying to visually show, hey, anything less than 2 here would work. So what we're going to do is, instead of shading in 2, we're going to leave an open dot here because 2 doesn't technically work. So I don't want to shade it in. And then I'm going to shade everything to the left because I'm saying anything less than 2 would work here. So basically what I'm doing for my reader is showing visually, hey, anything over here forever would work. You don't really need to shade like that, but that's what this is saying. Okay, so just a couple rules for you. Hopefully you remember these from Algebra 1, but in case you've forgotten. If we have the greater than symbol or the less than symbol, we're going to have an open dot. If we have the greater than or equal to symbol or the less than or equal to symbol, then we're going to have a closed dot. And the reason is we're just trying to show visually, hey, if it's greater than, if it's greater than or equal to or less than or equal to, then we would include that point in our solution set. So we want to close it off. That was our that was why we closed off on this example up here. That's why we closed that one off, because we want to include 3. We didn't want to include 2 here, so we left it open. Okay? And the last thing I want to talk about is whether or not to shade left or right. And this is a little complicated. It's a little more nuanced than you would like, okay? So if we have something like this where x is less than a number, I'm just going to say 7, or if you have something like 7 is greater than x, be very careful. These are saying the same thing, okay? This is saying x is less than 7. This is saying 7 is greater than x, which is actually literally saying the same thing. X is less than 7. If you get a scenario like this, then you're going to shade left. Because what we're saying is we want all of the numbers that happen to be less than 7. X is less than 7. If you get something like x is greater than 9 or 9 happens to be less than x, these are saying the same thing. X, the number that you're having question, is greater than 9. It's the exact same thing as this. X here is greater than 9. I worry when teachers say, oh yeah, these, if the symbol looks like this, then shade left. If it looks like this, shade right. And it's like, well, you gotta be really careful because they mean different things depending on where the X falls, right? Okay, so anyway, if this is the scenario, you're gonna shade right.